So here we are in our final section of the class, section 9.7 on Pascal's formula and the binomial theorem. So I know that we've seen these two things before, but we're going to connect them to some of the things we've been doing in chapter 9. So we have two objectives. One is to look at Pascal's formula. And then number two is to take a look at the binomial theorem. And if you don't remember these off the top of your head, great. We'll be going over them again. So we're going to start with a little example of some very specific combinations. So first we're going to evaluate n choose n. We're going to evaluate n choose n minus 1. And we're going to evaluate n choose n minus 2. So n choose n becomes n factorial over n factorial times n minus n factorial. Well, that's just n factorial over n factorial, which means 1. And that makes sense. If you have n things and you want to divide them up into n different categories or n different groups, you can only do that one way, everything into the one group. N choose n minus 1 becomes n factorial over n minus 1 factorial times n minus 1. Extend that out, factorial. Well, this just becomes n factorial over n minus 1 factorial, because n minus 1 is just going to be 1. 1 factorial is 1. And so this just becomes n. Right, so if you have n objects and you want to split them up n minus 1 different ways, there's only n ways because you leave one off every single time. And you can leave off one of all of your options, so for a total of n options. And then n choose n minus 2, n factorial, learned my lesson this time, this needs to be a big denominator, times n minus 2 factorial times n minus 2 factorial. This becomes n factorial over n minus 2 factorial times 2 factorial, which gets us to n times n minus 1 over 2. So you may see a pattern developing that we've seen already. These are summing, this was our formula for summing n squared things, or n squared. So what I'd like you to do is pause the video here and just work through and show that n choose n minus r equals n choose r. So, like I said, pause the video, try this out. It's short, it's sweet, you'll get it. I'll walk through it now. So n choose n minus r is n factorial over n minus r factorial times n minus n plus r distributing by negative factorial, which becomes n factorial over r factorial times n minus r factorial. Well, that's nothing more than n choose r. That's the formula for n choose r. So the purpose of this is to set up Pascal's formula. So n choose r is equal to n choose n minus r means that n choose n minus 2 is equal to n choose 2. N choose n minus 3 is equal to n choose 3, and so on. And so what we end up with is, when we start looking at these things, n choose n minus 1 is the same as n choose 1. So while this is on the right spectrum of making this thing very large, it's equal to the number of things making something very small, and they keep getting equal all the way to the center. If you think of Pascal's triangle. So what Pascal's formula says let n and r be greater than 0 and integers. With r less than or equal to n. Then n plus 1 choose r is equal to n choose r minus 1 plus n choose r. Now this may seem innocuous, but this is actually really an important result in combinatorics and counting. So we're going to prove this because we can prove it with this little result that you just did on your own. We can prove this. This nice, very important theorem only takes this one relationship. So we have n choose r minus 1 plus n choose r. We're going to go from right to left. Since it's an equality, we get to pick. And this way we know what this needs to look like. This has more information to work with and more things to reduce. So it'll be a lot easier to condense this than it would be to expand this one. So this is n factorial over r minus 1 factorial times n minus r plus 1 factorial plus n factorial over r factorial times n minus r factorial. So this piece and this piece, while similar, we're going to make them the same by getting a common denominator. So this is n factorial times r plus n factorial times n minus r plus 1. That's because this term here is only n minus r plus 1 on the top and the bottom, away from n minus r plus 1 factorial. And this term here is only 1r times it to get to r factorial. So we're multiplying the r to this one, and we're multiplying the n minus r plus 1 here and here. And so then we can group this as 1 r factorial over n minus r plus 1 factorial. And then we're going to distribute this n factorial. So we'll have n factorial times n, or n times n factorial, minus r times n factorial, plus r times n factorial, and then plus n factorial, all over our r factorial times n minus r plus 1 factorial. And then these will cancel each other out. And we'll have n times n factorial plus n factorial over that r factorial times n minus r plus 1 factorial. Well, we can factor the n factorial out, and we have n plus 1. And then on the bottom here, we have n plus 1 minus r factorial, rearranging those, times r factorial. But n plus 1 factorial, or n plus 1 times n factorial, is just n plus 1 factorial plus 1 factorial. And this then is n plus 1 minus r, grouping that up like this, factorial, times r factorial. And of course, that is nothing more than n plus 1 choose r, which is what we wanted from Pascal's formula. We wanted it to be n plus 1 choose r. And so we have our proof. So this style of proof is actually how we derive more relationships between certain combinations like this. So what I would like you to do is to use Pascal's formula. So you don't need to prove it, it's proven, not Parkel's. Pascal's formula to find a new formula for n plus 2 choose r in terms of n choose r factorial, n choose r minus 1 factorial. Why do I keep doing it? N choose r and n choose r minus 1 and n choose r minus 2. Got factorials on the brain. Doing it all last section as well. So when you have your final answer, your formula for n plus 2 choose r should have these three things in them, just like Pascal's formula for n plus 1 choose r has n choose r minus 1 and n choose r. So now when we have n plus 2 choose r, you're going to add a second term. And you're going to need to use this formula. So pause the video and try that out. I'll start walking through it now. So n plus 2 choose r by Pascal's formula is equal to n plus 1 choose r minus 1 plus n plus 1 choose r. But n plus 1 choose r minus 1, applying Pascal's formula to this, is n choose r minus 2 plus n choose r minus 1. And n plus 1 choose r, using Pascal's formula, is n choose r minus 1 so this would be plus down here, n choose r minus 1 plus n choose r. So this thing splits into these two, this thing splits into these two. And then we can rewrite that, n plus 2 choose r equals n choose r minus 2 plus 2 copies of n choose r minus 1 plus n choose r. Now this may look familiar to you as the factorization or the expansion of a plus b quantity squared. We have 1, 2 times it, and 1. And as it turns out, if you remember, Pascal's triangle was a way to memorize quickly and easily the coefficients for binomial expansion. And that comes from Pascal's formula, which led us to the binomial theorem. And the binomial theorem looks like this. Theorem. So given real numbers a and b and non-negative integers or non-negative integer n, we know a plus b to the n is the sum from k equals 0 to n choose k times a to the n minus k times b to the k, which, if you remember from your pre-calculus days, this gets expanded out to a choose a to the n plus n choose 1 a to the n minus 1 times b plus n choose 2 a to the m minus 2 times b squared plus dot 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 all the way to n choose n minus 1 a to the b times n minus 1 plus b to the n. That's our binomial theorem. Now what we usually leave off here is this coefficient is n choose n, and this coefficient, from what we started with, is n choose 0. Or actually, I have these reversed. This should be 0 and this should be n. Now, we leave these off in pre-calculus because, I mean, depending on your professor, I know I show this to them and then I say these are equal to 1, so we leave them off. But you can see these are getting wrapped in, like I was talking about, these things equal each other down to the middle. And we can write it this way because of this wonderful property that Pascal's formula gives us that allows us to expand it. These terms, Pascal's triangle is a simplification of these terms for when n is 2, when r is 2, when n is 3, r is 3, so on and so forth. But that's our binomial theorem in case we've forgotten. And it all comes down to Pascal's formula. So just to remind ourselves, I would like you to expand one quick binomial. So expand x minus 4y to the 4th using the binomial theorem. So I'll work through it, but you should pause the video and try this out. So according to our binomial theorem, x minus 4y to the 4th is x to the 4th plus 4 choose 1 x cubed times negative 4y plus 4 choose 2 x squared times negative 4y squared plus 4 choose 3 x times negative 4y cubed plus, I ran out of space here, negative 4y to the 4th. And simplifying, we have x to the 4th. 4 choose 1 we know is just 4. 4 times negative 4 is negative 16. X cubed y. 4 choose 2 is a lot bigger. And when you simplify that out, we get plus 96 x squared y squared. 4 choose 3 is even bigger than that. When that gets simplified, we get, it's not plus anymore, it's minus 256 x cubed y, x cubed, silly me, xy cubed, excuse me, and then 4 cubed, or 4 to the 4th, we get plus 256y to the 4th. And that's just applying our binomial expansion and getting our coefficients that way. Right? And if you remember the Pascal's triangle, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. That means we multiply 4 choose 1 is 1. Or I'm sorry, 4 choose 0 is 1. 4 choose 1 is 4. 4 choose 2 becomes 6. 4 choose 3 becomes 4. And 4 choose 4 becomes 1 again. So Pascal's triangle really is just a shorthand memorization tool for memorizing n choose r's. We just don't ever really focus on that so much. Usually we say memorize the triangle and you'll be able to expand any binomial. But that's where those coefficients come from. So the last thing we're going to do is use the binomial theorem and Pascal's formula in a more interesting way for our class level, that is. So we're going to show that 2 to the n equals the sum from k equals 0 to n of n choose k. So this is a much more interesting formula. And this comes down to using the binomial theorem in a way that in your pre-calculus days and your algebra days you might not have thought to use it. So 2 to the n is really 1 plus 1 to the n. Well, now we have a binomial expansion. Remember, a and b just need to be real numbers. We typically have them as variables, but they don't need to be. So using our binomial theorem, this is 1 to the n plus n choose 1 times 1 to the n minus 1 times 1 plus n choose 2 times 1 to the n minus 2 times 1 squared plus dot 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 plus n choose n minus 1 times 1 to the n minus 1 plus 1 to the n. But all of these powers of 1 to the n minus 1 times 1 just becomes 1 to the n. 1 to the n minus 2 times 1 squared just becomes 1 to the n. And we know every power of 1 equals 1. So this really becomes 1 plus n choose 1 plus n choose 2 plus dot 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 all the way down to n choose n minus 1 plus 1 again. Well, if we want this to work, we need to have it equal this. But this is 1 is n choose 0, n choose 2 plus dot dot dot, n choose n minus 1. And by Pascal's formula and the property that you showed earlier, n choose 0 is the same as n choose n. N choose n. Well, that's nothing more than the sum from k equals 0 to n of n choose k. We're just adding up every single choice all the way up to n. And so we've proven that. So this is a way that we can use the binomial theorem at this level to prove a interesting property like this. But this is the final section of the class. There will be no more lecture videos after this. So this is the end of chapter 9 and the end of our lecture material.